I'm Angelica Obciana of Section EG, and this is a group's problem. At the year 2075, a new virus dubbed as Virus C has spread across a small city with a population of 90,000, infecting only one person at the start. After 10 days, the number of people infected was 51. How many people were infected after a month has passed? If nothing will ever be done to prevent the disease, will all the people actually get infected as time approaches infinity?
So, first, it was given that the city's population was 90,000. So, we represent that with the variable A here. And it was also given that there was only one person infected initially. So, we represent that with at t is equal to 0, x is equal to 1, where t is the number of days and x is the number of people infected. After that, it was also stated in the problem that there were 51 people infected after 10 days. So we represent that with at t is equal to 10, x is equal to 51. So the first question is, how many people will get infected after 30 days? So we represent that with at t is equal to 30 days, what would be x? The second question is, will x be equal to 90,000 as t approaches infinity?
Okay, so we know that dx dt equals to kx a minus x is the equation for the rate of spread of an infection in a given population. X being the number of people infected, t is the time elapsed, k is the proportionality constant, and a is the initial population, where it is 90,000. So we need to get x as a function of time, and we put x on one side and everything else on the other side to do that. So here, we move x times 90,000 minus x here, and dt here. So we need to integrate both sides next. In order to integrate this side, we need to do partial fractions. 1 over x times 90,000 minus x is equivalent to a over x plus b over 90,000 minus x. Second equation, we can get that a is equal to 1 over 90,000. From the first equation, we can get that b is equal to a, which is also equal to 1 over 90,000. Rewriting that equation will give us this. In fact, 1 over 90,000 is factored out because it's a common constant. And integrating this will give us ln of x over 90,000 minus x, subtraction of two logarithms. So that's why we can shorten it to this form. And integrating the right side will give us kt plus c. So if we multiply 90,000 on both sides, we remove 1 over 90,000 on the left side and we multiply 90,000 on the right side, 90,000 kt plus c1. C is an arbitrary constant, so we can just do anything with it. So we can just name it as c1. Removing the logarithm, we get x over 90,000 minus x is equivalent to e raised to 90,000 kt c1. Multiplying 90,000 minus x on both sides, we remove it on the left-hand side, and we get 90,000 times e raised to 90,000 ktc1 minus x times e raised to 90,000 ktc1. Moving this on the left-hand side of the equation, we can factor x, and we divide both sides of the equation with 1 plus e raised to 90,000 ktc1. We get x as a function of time. So now we need to find k and c1. In order to do that, we need to use our two initial conditions given in our problem. Let's use our first initial condition. T equals to 0 and x equals to 1. If we plug everything here, we'll find that k is multiplied to 0, so we can find c1, which is 1 over 89,999. For our second initial condition, t equals to 0, t equals to 10, x equals to 51, we can see that k is now the only unknown variable. And by doing all these algebra, we can arrive that k is equal to 4.37 times 10 to the negative 6. Now that we have k and c1, we can find x at t equals to 30. So when we plug in everything, we'd get x equals to 53,657 people approximately. And for the side question, given all these test values, no, we won't reach 90,000 given that we don't do anything, because as t increases, x just approaches 90,000. But it won't arrive at 90,000 as given by these test values. So to illustrate that graphically, we would have an abrupt increase here, but it was eventually straightened out there.